Hi everyone! Today's lesson is on periodic trends. You will use the periodic table as a model to predict the relative properties of elements based on the patterns of electrons in the outermost energy level and the composition of the nucleus of atoms. The objectives are to demonstrate the formation of ions, define atomic radii, ionic radii, ionization energy, electron affinity, and electronegativity. Compare the periodic trends of atomic radii, ionization energy, and electronegativity, and state the reasons for these variations. Then you will compare the atomic radii, ionization energies, and electronegativities of the d block elements to those of the main group elements. Do you remember how to tell the number of valence electrons for elements in the s and p blocks? It's based on the group number. Elements in group 1 have 1 valence electron. Elements in group 2 have 2 valence electrons. When you get to groups 13 through 18, you just subtract 10. The one exception is helium with only 2 electrons, but that is a full valence. The rest of the noble gases have 8 valence electrons, which is the goal of all atoms. They all want to get to 8. That's the octet rule. The main group elements are called the representative elements, and those are the ones you can predict the valence electrons by looking at the periodic table groups. Remember, the Lewis dot diagrams show the valence electrons for the elements of the main group. The transition metals would be in between, like beryllium and boron, there's a big gap. When you're looking at electron configuration, you can determine valence electrons by looking at the highest occupied energy level, s and p orbitals. So if you look at this electron configuration for gallium, it's 4s2, 3d10, 4p1. 4 is the highest in energy level, and the number of electrons is 3. So that means there are 3 valence electrons. Gallium is also in group 13 on the periodic table. There's a pattern in electron configurations for main group elements. So if you look at the electron configuration for a group 1 element, if it's in the first energy level, 1s1 would have 1 valence electron. If it's whatever energy level it's in, n can be 1 through 7, and it's in s2, then there's 2 valence electrons. If it ends in p1, then you add the s and the p of the highest energy level, and that's 3. Highest energy level n, 2s plus 2p is 4. That's in group 14. And it continues until you get to 8. So how do you determine valence electrons in the d block, the transition metals, and the f block, the intertransition metals? Most transition metals in the d block have 2 valence electrons. The valence electrons are the sum total of all the electrons in the highest energy level, principal quantum number n. Most transition metals have an electron configuration that is ns2 and then n-1d. Remember, it goes down by 1 in the d block, the energy level does. So those ns2 electrons are the valence electrons because this will be a higher number than the d block, the n number will. Example, the electron configuration for iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. 4 is the highest energy level. There are 2 electrons in the 4 energy level in the s block. Exceptions. Some atoms would be more stable by filling a d block and taking out electrons from the s block. So for example, chromium has 1 valence electron, as does copper. So the configuration, instead of saying argon, this is the noble gas before chromium, and instead of saying 4s2 3d4, it'd be better to put one electron in each of the d orbitals and give the s orbital just one. So half filling the d orbitals is more stable than having a full s orbital and only a partially full d orbital. Same with copper. It's more stable to completely fill the d sublevel than to leave the s sublevel full and then the d sublevel only partially full. Let's look at some orbital diagrams to better understand this. So chromium has an atomic number of 24, that's what Z equals. Argon is 18, right? So after 18 for chromium, it's 4s1 3d5. Why? Because it would be more stable to give each of these orbitals one electron than it would be to pair up the 4s and only partially fill the 3d orbital to 4 electrons. Same with copper, except for instead of 3d9, it becomes 3d10. So completely fill this d orbital and then partially fill the s orbital. Now, chromium and copper can vary in their number of valence electrons when they form chemical bonds. Here are some more exceptions. Copper, silver, gold, palladium, chromium, and molybdenum all follow different rules. The significance. What is the significance of knowing the number of valence electrons? Well, the goal of most atoms, except for hydrogen, lithium, and beryllium, is to have an octet, or 8 valence electrons. This is accomplished by giving or taking electrons. When this happens, ions formed. Atoms that have gained or lost electrons are ions. Metals give electrons. Nonmetals take electrons. Hydrogen can lose one valence electron to become the hydrogen ion, but it could gain one electron to form the hydride ion when it bonds with a metal. Cations lose valence electrons. They become positively charged. That means they will have more protons than electrons. Metals tend to lose electrons, forming cations, positively charged ions. Anions are when atoms gain valence electrons. They become negatively charged. They have more electrons than protons. Nonmetals tend to gain electrons, forming anions. So remember, the metals are everything colored in blue on this periodic table to the left of the stair-step line. The purple ones are the metalloids, and then the orange ones are the nonmetals. So the metals all tend to form positive ions, and the nonmetals form negative ions, except for group 18. Group 18 are the noble gases, and they don't need to gain or lose any electrons because remember, they already have a full valence. I also want you to notice that the main group elements are lettered and numbered 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. The transition metals, they are numbered B. 3B, 4B, 5B, 6B, 7B, 8B, and then these are considered 1B, 2B. How does a cation form? So let's look at a specific example of lithium, a neutral atom. It has 3 protons and 4 neutrons in the nucleus, so an overall positive 3 charge in the nucleus, but the cloud has 3 electrons in it that goes around the nucleus. So positive 3 and negative 3 is 0. That makes it neutral. When it loses an electron, it becomes positive because now it's got 3 protons and 2 electrons, So it's got one more positive charge than it does negative. And so that's what gives it an overall +1 charge, the lithium ion. I want you to also notice when you lost that one valence electron, the electron cloud gets a little bit smaller. That's going to be important when we talk about ionic radius. So here is a demonstration of cation formation. This is sodium, the atom. It has one valence electron. The valence electron is lost when it forms an ion. Notice the size of the ion got a little bit smaller because the remaining electrons are pulled in closer to the nucleus and the size decreases because of this. There's a smaller sodium cation than there was a sodium atom. An anion forms when atoms gain electrons. So on the left we have the oxygen atom with 8 protons and 8 electrons. On the right side we have the oxide ion, still with 8 protons, but it gains 2 electrons, giving it overall -2 charge, because now there are 10 electrons and 8 protons. So it's a little bit more negative than positive. Here's a demonstration of anion formation. You have 17 protons. This is chlorine. It has 7 valence electrons. It would like 8, so 1 electron is added to the outer shell. And so this increases the ion whenever you add this electron. I don't know why this isn't working, but if this electron added here, then it would repel a little bit more with these other electrons, and so it would produce an ion that is slightly larger. Okay, there is a periodic trend in ionic charges, and we've labeled this on a periodic table before. If you haven't, you should. At the top of group 1, I usually write them at the top. I would write a 1+. At the top of group 2, I would write a 2+. You do not write any charges above the transition metal because they tend to have more than one oxidation number. You show the oxidation number with the Roman numeral. More about that later. Group 13, 3+. Group 14 is a weird one. Because there's 4 valence electrons, it could either lose 2, or it could lose 4, or it could gain 4 to get an octet. Group 15 gains 3 electrons. It goes from 5 valence to 8 by gaining 3. Group 16 has 6 valence, so it needs to gain 2 electrons, -2. Group 17 has 7, so it needs to gain 1 electron, 1-. And then the noble gases are 0. The lanthanides and actinides have these charges, and we don't really use them in chemical bonds too often, but just FYI, 3+ or 4+.